Hello student, to our course Wave Optics, where we today have lecture number 9, and in this lecture we are going to discuss about the group and phase velocity, the concept of group and phase velocity. Okay, so let me start with the concept that we initiated in the last class. So today we have lecture number 9. So in the last class we discussed about the concept of superposition of different waves. So our basic concept was superposition of waves, and in order to study that, in the last few classes we superimposed two waves and their frequency same in the frequency. So now what we do today, we will going to superimpose two wave, or we add two wave whose frequency is slightly different. So we will do today the addition of, this is under superposition of wave, but two different frequency we are going to add two wave having two different frequencies. So addition of waves with different frequency. Suppose we have two waves, say E1 which is equal to E10 cos of K1x minus omega 1 t. Previously it was simply omega, but now we are going to discuss what happened if we add two wave. So instead of having one wavelength, now we have two different wavelengths for two different waves. So next is E20 cos of K2x minus omega 2 t. So their amplitude maybe we consider to be same for simplicity, and their wavelength is different. So I can take their amplitude to be same. So I can write E10 is equal to E20 is simply, say I write E10 because it is same. So I write E20 simply E10. So that is the condition we put, that their amplitudes are same. Now the resultant wave will be E1 plus E2. Since their amplitudes are same and we call it E10, the amplitude of E1 wave, which is same as E2, so I write E10 and then simply write cos of alpha plus cos of beta, where my alpha is equal to K1x minus omega 1 t and beta is K2x minus omega 2 t. This is the value of alpha and beta, and now we simply try to figure out what is this value. So, simple addition of cos alpha and cos beta gives us 2 of E10, then cos function of alpha plus beta divided by 2, and then this is cos A plus B. So, cos A plus B by 2 and cos A minus B divided by 2, that is the next one. And now alpha plus beta and alpha minus beta I can calculate because it is already defined in here, and if I do, we are going to get this 2 of E10, it will be cos of alpha plus beta, then simply K1 plus K2 divided by 2x minus omega 1 plus omega 2 divided by 2t, that is the first term, multiplied by cos of K1 minus K2 whole divided by 2x minus omega 1 plus omega 2 whole divided by 2 t. So, that is the total term we have when I simply add two wave having this form, two different waves. Their amplitudes are same, that is the condition we have, but their wavelengths are different, and in that case if I add these two waves together, then this is the resultant wave we get. Okay. Now, I can define, so whatever the terms we have, we can define like omega p, that is the sum average omega that we had. Similarly, I can define Kp, which is the average of the propagation constant of these two waves divided by 2. Also, we can write omega g, that is the difference between these two. So, I have omega 1 minus omega 2 divided by 2, and kg I define K1 minus K2 divided by 2. So, we just defined few more parameters, few more variables, omega p, kp, omega g, kg, but they are related to the initial frequencies that the wave had, that is omega 1, omega 2, and the initial k vector they have, the propagation constant value they have, which is K1 and K2. So, if I write all together in this new notation, then my ER become 2, it becomes 2 E10, that is the amplitude, and cos of Kp x minus omega p t multiplied by cos of kg x minus omega g t. So, we can see that two propagating wave with different frequency, when we add together, then the resultant wave is also propagating, but it has the amplitude. If I write this portion as an amplitude, the amplitude is also moving. What is the meaning of amplitude and what is the meaning of propagation, we are going to understand clearly. So, before that we can see what is the frequency. Here we can see that this function cos kp x minus omega pt, this is a propagating wave and this is also propagating. So, initially we have, so let me picturize what we get. So, we have two waves with equal amplitude but different frequencies. So, this is my say E1 and another wave with relatively say higher frequency is E2. What we did is we add these two by using the superposition principle, that is we simply linearly add these two and I get two waves with the multiplication of this cos function, suggesting that this resultant wave is also propagating because it is having the form kx minus omega t form. Well, this wave is called the carrier wave. Having a frequency omega p, and omega p, as I mentioned here, it is omega 1 plus omega 2 divided by. So, carrier wave is a wave having a average frequency, whatever the frequency we have for E1 and E2, the frequency of the carrier wave is average of that, and it is moving with a velocity. It is moving with a velocity if I write Vp, that velocity is omega p divided by kp. This is the velocity at which this carrier wave is moving. Also, we have another part of this wave, and this part which is having relatively lower frequency. If we look omega g carefully, omega g is the difference between these two, related to the difference between the two waves, the frequency of the two waves. So, this is called the envelope wave. This is the envelope wave and moving with a velocity I write Vg is equal to omega g divided by kg. This is the velocity at which it is moving. Clearly, it is given that the velocity of these two are not same. It can be same in few cases, but in general this is not same. And omega p is much greater than omega g. So, that means the frequency that the carrier wave is having is much higher than the frequency the envelope wave we have. Now, if I picturize that what is these two waves and how it should look, it will be like this. So, yeah. So, let me draw. In the same figure, I will draw we're going to draw the two waves. So in one case, so let me fix the amplitude. And this is a wave having high frequency. This is a one wave, and this is my E1. Another wave I also draw whose frequency is less, and it is something like this. Okay, on top of that I draw, and this is my E2. So if I add this E1 and E2, the resultant wave will have a form like this. We have an envelope like this, and inside this envelope we have the carrier wave. The solid line that I am drawing here will be the structure of the resultant wave that one can expect. So, this is along x direction, and this is moving. This is moving. This is the resultant one. So, the resultant one means ER, which is equal to E1 plus E2. And ER is a moving wave. It is having a modulated amplitude. Inside this envelope, we have the distribution as well, which we call the carrier wave, having a frequency omega p, which is omega 1 plus omega 2 divided by 2. And also there is a modulation in amplitude, and it is periodically modulated. We call this envelope function through which it is modulated, and this envelope function on envelope wave is having a frequency which is omega 1 minus omega 2 divided by 2. So, and this is also moving in this direction, in one direction. Now, the point is, what should be the velocity of this envelope that is moving, and what should be the velocity of this carrier that is moving. Already it is mentioned that the carrier wave will go to travel, so with the velocity. So, let me write here. So, the carrier wave for carrier wave, the velocity, if I define Vp, this is W omega p divided by Kp, and this is essentially omega 1 plus omega 2 divided by K1 plus K2. Now, this value is nearly equal to omega by k, where omega, I mean, this is the where omega is the average one and k is somewhere. If I just write the average of omega and omega 2 is omega p, so I write omega and k and k2 the average of that thing is k. So, this value will be simply omega divided by k. Well, on the other hand, the envelope wave have a velocity Vg, which is omega g divided by kg, and that is essentially omega 1 minus omega 2 divided by k1 minus k2, which is delta omega divided by delta k, where delta omega is the difference between these two frequency and delta k is the difference between the wave number they have. So, this is essentially d omega. If they are small, then I can write it as d omega dk. So, this velocity is a special name, it is called the groove velocity. And the carrier wave, which is propagating with a velocity omega divided by k, is called the phase velocity. So, this is called the phase velocity. So, these two velocity we define, in one case it is omega by k and another case it is d omega by dk. Now, in this wave, whatever the drawing we have, we can see that the envelope, that is the tip of this thing, is moving with a velocity Vg, and also the carrier wave is also moving with a velocity which is Vp. Now, we can, from the expression we can write that Vp is simply omega by k and Vg is d omega by dk. So, Vg I can write in terms of Vp. So, Vg, which is d omega by dk, I can write d dk multiplied by Vp into k. So, this essentially give us Vp plus k into del Vp dVp dk. So, this is the relation between the groove velocity and the phase velocity. So, groove velocity is equal to phase velocity plus k multiplied by the derivative of the phase velocity with respect to k. So, if we had a situation when the phase velocity, the change of phase velocity with respect to k vanishes, then one can simply have then we can have Vg is equal to Vp. That means the phase and groove velocity are same. So, normally this case happen when the light or the optical wave is moving through a vacuum or a free space. Vacuum or free space. Then Vp is equal to Vg and they are equal to C. So then what happened, that Vp is equal to Vg and they are equal to the value of the speed of the light C. But the problem is completely changed. The problem is different when we have a dispersive medium. So what is the meaning of dispersive medium? That means we have a medium with a refractive index. We have a medium with refractive index more than 1. So for a dispersive medium, what we have, Vp is no longer C, it is basically C divided by Nk, because refractive index is a function of the propagation constant or wavelength. So that means in dispersive medium, Vp is less than C. So refractive index, as I mentioned, is a function of wavelength or K. Then Vg, from this expression we had, so Vg was how much? It is Vp plus K into dVp divided by dk. So Vp I know what is the functional form, so that I am going to put, and also put, okay, let me do that first. So I have Vp plus K, and then I need to make a derivative. So n is a function of K. So what I do, I will write that d of n Vp and d of n dk. Should be d dk. So this quantity, if I execute this quantity, it should be Vp and then plus K dVp dn. From this expression I simply have minus of C n square, and then we have dn dk. So from here I can also find that C by n, I can write it is Vp, and this expression simply gives us Vp. If I take Vp common, then 1 minus K by n dn dk. But normally what we do, we do not put dn dk because n is a function of lambda. So normally we try to write down everything in terms of lambda. So this expression we slightly change. as per our convenience. So, let me write it down. So, we have Vg is equal to Vp 1 minus 1 minus k by n, we have dn dk. Instead of write this, what we do in this way. So, k I write as 2 pi by lambda. So, dk d lambda will be minus of 2 pi by lambda. And if I replace this derivative, Vg will be Vp 1 minus k, I replace 2 pi divided by lambda, then it is 1 divided by n, and this derivative I write dn d lambda, because n is essentially a function of lambda. We know the explicit form of n as a function of lambda, we will show in the next class maybe. Then I write dk d lambda, which is dn d lambda rather, d lambda dk here I write. So, let me do that, d lambda dk. So, d lambda dk I replace it from here. So, we have Vg equal to Vp 1 minus 2 pi divided by lambda into 1 by n dn d lambda, and this quantity is minus of lambda divided by 2 pi. Here should be a lambda square. So, it should be lambda square by 2 pi, and essentially we get Vp into 1 minus, this 2 pi will cancel out, 1 lambda will cancel out, this minus will be plus. So, plus lambda by n, then dn d lambda. So, we have dn d lambda. So, this is the expression we have, which shows how the quantity Vg and Vp are related to each other, that is the group velocity and phase velocity is related to each other. And we find a very important term, that whether the group velocity and is equal to phase velocity, under that condition what happened, the dn d lambda has to be 0, that means n should not be a function of lambda, and it only happens when we have the value of n equal to 1, that is in free space or in air. So, where the refractive index does not change with lambda, in that case we have Vg equal to Vp, that we know. But what happened when we have a component like this into the equation, that means when we deal with the velocity of the light in a medium, then that medium should have a characteristic form in terms of its refractive index, and if you know the refractive index as a function of lambda, then from this expression we can calculate the group velocity of the light. So, when the light with different frequency is passing through that medium, the phase and group velocity, they will differ, and also the group velocity is a function of lambda. So, different wavelength will travel at different speed, and that is the phenomena we call as the dispersion, which is very important when we discuss the aspects of light as a wave, and if it is passing through a dispersive medium, then the velocity of the light for different frequency component will be different, and that is why what happened, we will going to get a very important phenomena called dispersion. So, today we do not have much time to discuss the phenomena of this dispersion. In the next class, we are going to discuss in detail the phenomena dispersion, and then we will discuss more about the material aspects of the dispersion, how the refractive index is related to lambda, that we are going to discuss, and then go forward with other topics. With that note, I like to conclude here. Thank you very much for your attention, and hopefully we will going to see in the next class where we are going to discuss about the material dispersion in detail. Thank you very much. See you in the next class.